in mind that we're trying to answer the question, when are closed forms exact? Right? And the dual of this is, when do I have, when are cycles also boundaries? Okay. So we've kind of answered when our cycle is bounded. I told you one tractable space, and if the space is tractable, then if I have a cycle, then I can write it as the boundary of some higher one higher chain. The question about when are closed forms exact is a little bit more tricky. However, we can make some headway into this through something called Durand's theorem. And Durand's theorem tells us how the homology of forms is related to the cohomology of chains. Okay. In many senses, the theory of cohomologies is richer than the theory of homology. In the sense that there's additional structure that is hard to make manifest in homology groups, but that emerge quite naturally in cohomology. One is that if I give you an n-dimensional manifold, right, then I have 0 chains, 1 chains, 2 chains, etc. If I look at those chains modulo, if I look at the subset of the chains that are cycles modulo boundaries, I can construct homology groups. So I get H0, H1, H2, all the way through to Hn. If I add all of these guys up together, if I take the direct sum of all of these guys, they give me another space. That space has a structure in a homology theory of a ring. Right? So a ring is a generalization of a group with one more operation. So where I have group multiplication, I have group addition, and group multiplication for a ring. And it turns out that the direct sum of all the homology groups, give you a cohomology groups give you a cohomology ring structure. This kind of ring structure is very difficult to make manifest in the theory of homologies. On the other hand, there are things that you can do with homology groups because they tell you about forms, and forms are really things you differentiate and integrate, right? That you can't do with chains. It's hard to talk about multiplication of surfaces, right? But it's easy to talk about multiplication of forms, right? So we'll see all these structures emerging now. So I told you the last time that I have this inner product that I can define between the set of homologies and the set of cohomologies, and they took the homology, the R homology group, crossed with the R cohomology group, and mapped it to the reals. And then if I thought about this bilinear map as a linear map, let's say from the set of homologies to the reals, or the set of cohomologies to the reals, both of those gave you well-defined linear maps. And so that would hint then that the P homology group was dual as a vector space to the P cohomology group, if I define them over R, say. Okay? But in order to prove that these two are in fact vector space duals, right, I needed for this linear map to be of maximal rank. In other words, the dimension of the two must be the same. This is a highly non-trivial statement. Right? To prove this statement, you need to prove Durand's theorem. So I'm not going to do that. I'm going to state Durand's theorem, and then we're going to explore some consequences of it. So, a statement of Durand's theorem without proof is that if I've got some compact manifold, this is really the crux of the story. For a compact manifold, these two dimensions are actually equal. Okay, so if I've got a compact manifold, then the set of cohomologies and the set of homologies are both finite dimensional. And this map that we talk about, this capital lambda that we talked about last time, capital lambda is then bilinear and non-degenerate, which means that indeed the R cohomology group is dual to the R homology group as a vector space. Okay, so the Ron's theorem says that if M is a compact manifold, then H R M and H R M are finite dimensional. And lambda takes H R M plus H R M to R is bilinear and non-linear. Implies that H R then we define over the rails if H R M R J. Still online? Yes. Something on the last. I think this is the first one. Yeah, so before exploring some of the consequences of this statement, let me just define something we're going to use. Well, I don't think I'll get to get, but one of the things that we'll get to in the online extension of this course is curves that intersect on manifolds. And for that, this concept is quite important. And this is the idea of a period. So the period of a closed P-form over some cycle is the following integral. If I take the P-form omega and I integrate it over the P cycle C, I'll get a number. Yeah. That number we will call period of the P-form. The period of the P-form has the following properties. If omega is an exact form, so an element of VR of M, or C is a boundary, so it's an element of V subscript R, then either one, the integral of omega over c is the integral of d alpha over c. It's omega in exact form, then I can write it as d of something. And then by Stokes' theorem, this is the integral over dc of alpha, let's see the cycle, that's 0. Or the integral of omega over c is the integral of omega over the a, say, because this guy is boundary. Again, by Stokes' theorem, this is the integral over a of d omega. But omega in the closed p form, so that's 0. Either way, period vanishes. So now suppose that M is a compact manifold. Now suppose that M is compact and K is the, let's say, odd Betty number. Okay, so recall the Betty number is the dimension of a column. Okay. And K is the odd Betty number. Now I'm going to choose C1 to CK to be cycles, R cycles on M. And I'm choosing them such that the equivalence class of CI is different from the equivalence class of CJs for all the J's going from 1 to K. From 1 to K. So the ROM tells us that lambda, this inner product that we define, bilinear and non-degenerate. Right. This thing is non-degenerate. Which means that if we think of lambda as a linear map on H R, superscript R, then this is a linear map on H superscript R, and the kernel of this map consists of the trivial element, which is precisely the cohomology class of exact elements. In other words, a closed R form, let's say psi, and closed R forms of the element of, let's say, R, M, is exact if, and look here, it's integral over all the CIs, I'm going from 1 to k, valid. So here's a very precise, very concrete thing that you can calculate, tell you by the Raoult theorem, when a closed form is exact. It's exact if every single one of these CIs, right, I calculate in this integral and it comes out to be 0. If it's non-zero, again, go back a couple of lectures, non-zero integrals are obstructions to these topological things. If it's non-zero, then I have an obstruction to this exactness state. Right? But if it is 0 for all of these integrals, then Raoult's theorem tells me that this closed form must also be exact. That's consequence number 1 of Raoult's theorem. But Raoult's theorem also ensures us that given a basis for the R homology, some set of TIs, I can also choose a dual basis, let's say omega I, the R cohomology. And I'm guaranteed by the fact that this is a bilinear non-degenerate map, that if I calculate lambda, the equivalent stuff of the CIs, the equivalent stuff of the omega J's, right, then I can normalize these guys so that that comes up to be delta I. Okay. So, I mean, the things that I'm saying right now might sound deep. They're really not. They're essentially just other linear algebra. These are statements that you're already familiar with linear algebra, just not crazy in this one. Because essentially what we're doing here is working with linear vector space. So let me write that down. Given a basis for HR of n, we can always find a basis, a dual basis omega I for R of n such that lambda of Ci omega j is delta ij. So what does this mean? Right. So now suppose I take this basis and I take a linear combination of the basis. So I define some R form omega as the linear combination, say AI omega I. I goes from 1. Okay. Any linear combination you want, any set of AIs, I don't think you can. Right. Just take these basic forms and I just add them up with some set of globals. Then I go ahead and I calculate the integral of this omega over the CIs. And this is the integral over the CIs of the sum over J, AJ, omega J. Which is sum. There's the sum over J of AJ integral of omega J over CI. This is just delta IJ. This is sum over J of delta IJ AJ, which is just AI. So let me do an example to illustrate why all these statements are useful. So one reason they're useful is because it's bloody hard to calculate homology classes. So any trick you can find to help you calculate homology classes as a mathematician is a useful trick. And this gives us a very useful trick for calculating homology classes. For example, one of the things that we know is that if I have a connected matrix, then that counts to be the dimension of the zero homology class. Zero homology class. Okay. And in particular, if the manifold M has n connected components, then the following is true. H naught of M is then the sum, the direct sum of R copies of R, if we take R to be the prototypical example, real one-dimensional space. Okay. So, because of the way chains work, because of the way surfaces, because of the way manifolds work, right? We counted and we showed that if there's you get one copy of R for each connected component. So if my manifold can be split up into n connected components, then that's what H naught of M is. Remember that our goal here is to find a way of calculating the homology groups and cohomology groups. Okay. Well, what Durand tells us is that if I know this guy, then I automatically know this guy. I don't have to do any computations about forms, zero forms, functions. Right? It's because these two are dual to each other. Similarly, H1 of S1 is H1 of S1. And both of these are just R. One of them I can calculate trivially, the other one is by Durand's theorem. Another consequence of Durand's theorem is that if these two spaces are dual to each other as vector spaces, then they must have the same dimension. If they have the same dimension, that means their Betti numbers must be the same, or rather, the analog of the Betti number for cohomology must be the same as the Betti number for homology. Okay, so Durand also implies that the subscript, superscript of M, which I'm defining this in analogy, the dimension on page R of M. And by Durand, this is the dimension of H little r, lowest subscript R, which is the Betti number, the R Betti number. Well, this gives us another way then of writing the Euler number, Euler characters. So this says that I can then write the Euler characteristic as a sum from r equals 1 to the dimension of the manifold, alternating sum 1 to the r of Br of M. And again, I want to emphasize this fact. This Br of M, the dimension of H, this R of M, right, is an analytic statement. It's a statement about solving differential equations. But to determine what this guy is, I'm asking questions about things that look like d omega equals 0. This is a set of differential equations. Okay? The thing on the left-hand side is a logical quantity. It has to do with integrals. It has to do with information about the entire manifold. Okay. Remember, it's the alternating sum of R chains of the manifold. So you look at points, you look at lines, you look at points, you look at curves, you look at surfaces, you look at volumes. These are extensive objects. So the thing on the left-hand side, topological. And the thing on the right-hand side is analytic. The statement about geometry. So this is a geometrical. Right? And this is precisely the statement that you would make in differential topology. It's about using local information that you get from solving differential equations to say things about the global properties of space. Okay. And again, we've just been talking about spaces, about Riemannian spaces. All of these arguments can be extended to Lorentzian spaces, in other words, to space and time. So let me summarize that. So in summary, we have a chain complex, and we have a Durand form complex. Chain complex C of M and the Durand complex of the star of M that are the corresponding spaces together with maps between the spaces that are following. C R minus 1, C R, CR plus 1, etc. And I go between CR and CR minus 1 with boundary operator dr, R plus 1, to R, with dr plus 1. Similarly, I have the spaces omega R minus 1, omega R plus 1, and the exterior derivative operator maps me between these spaces, and so dr minus 1, dr, etc. And I have the associated homology group, or homology group, HR of M as the quotient of Z R M mod BR of M, and this is kernel of BR mod image of the plus 1, and R cohomology group R of M equal to ZR of M on BR and this is the kernel of B1 mod the image of DR. So as I mentioned, beginning of this lecture, the wrong cohomology groups have a rich structure that's sometimes hard to manifest in homology groups. Again, the difference between these two is in the one, you're working with surfaces and lines and telling you about adding lines and adding surfaces and multiplying surfaces, something. Whereas in the other one, you're working with forms. The forms are things that you different, and you add, and you subtract, and you multiply. So, in some ways, this is why cohomology groups have such a rich structure. Because they're dual, they both have a rich structure. It's just easier to manifest in the one. Okay, so the statement then is that the wrong cohomology has a rich structure that is manifest. For example, I want to look at two things in particular. So suppose I've got some compact manifold, some compact m-dimensional manifold. So again, let M be compact with dimension M. And let's take some representatives from the cohomology groups. Right? So I'm going to let omega be some representative from HP of M, and I'm going to let theta be, well, I'm going to take theta from HM minus P of M. The following is true. If I take the great product of P form and the M P form, since the degrees of these forms add, this guy is an M form. M form, non-vanishing, because I'm sampling them from H from the molecules. On the whole manifold, means that it's going to be proportional to the volume. Right? So up to that proportionality, this thing is the volume form. So it's like a TV. So now we can define in a product takes HP M plus HM minus P M R by on omega and theta as the integral over the manifold of omega to any. Okay. This inner product has the property that it is bilinear, it is non-singular, which means that that inner product only vanishes when both eta and omega is are vanishing. Okay. The inner product is bilinear and non-singular means this using notation there, I really mean omega equals 0 and eta equals 0 because they're different manifolds. Okay. But what this means is that this defines a duality from HP to HM minus. In the same way that we discussed the duality that Jerome implies. This says that HP of M is a dual to HM minus P on M. This is called Poincaré. And in particular, Poincaré duality implies that BP is B M minus P, the dimensions of these two cases must be the same. And in conjunction with Durand, this tells us that the Betty numbers, P Betty number, and the M minus P Betty number must be the same. So that's very cool. So now we have a relationship between between upper and lower Betty numbers, but also between the Betty numbers of BP and its complement in an m-dimensional manifold, Pn minus P. So here's one of the really interesting things that you can do with this. Okay. Remember, I said that when I sum all the Betty numbers, okay, I get topological information about the space. In particular, the Euler number, the Euler character, is related to the genus of manifold, number of handles and the number of holes. Okay. So here's an interesting consequence of this thing. My claim is that that statement necessarily means that if I have an odd dimensional manifold, any odd dimensional manifold, its Euler characteristic has to be 0. Let me show you why. So the claim is that phi of m is 0 for any odd dimensional manifold. Yeah. So let's prove that. So as I said, phi of m, we always make a sum minus 1 to the r minus 1 to b of b. So this is b naught minus b1 plus b2, etc. I don't really care whether I write that sum forwards or backwards. So let's do that. So this is the half of the sum P plus, write the same thing out backwards, minus 1 the m minus p m minus. Okay, so all I've done is I've taken that same series, written out once backwards, once forwards, because I've added the same thing twice. I divided by 2. So that's a half. Sum minus 1 to the p dp. And then I'm going to assume that m is an odd dimensional manifold. Means that I can write this m as uk plus 1. So I'll take out the minus 1 to the plus 1. That's nice. Sum of minus 1 to the 2k minus p. And minus 1 to the 2k is 1. So this is minus 1 minus p, which is the same as minus 1 to p. And then bm minus p. But bm minus p is the same as bp from what we just showed. That's b. That's 0. Right. So just using the duality between homology groups, between cohomology groups, right? We've managed to establish that any odd dimensional manifold you can think of will have vanishing Euler character. And again, the Euler character is related to the genus of manifold. Okay. So the genus tells me about things like holes, handles that these manifolds have. Okay. So we've just shown in 1+2, just using this idea from homology, that any odd dimensional manifold must have vanishing Euler character. And with that, I would like to end. Right. So as I said, I will be putting up you missed the part. I'm too sorry. I will be putting up the